Okay. Suppose if you take annual process, okay, this is annual means this is p-type substrate. Okay, here annual means we can fabricate p-mass. Can fabricate p-mass, and here p-type substrate means can fabricate here n-mass. Okay. Here this is p-type substrate. Here well is n. So here we can fabricate p-mass p-mass and here can fabricate n-mass. Okay. Here what is the disadvantage or some issue in the p-well or n-well processes? Okay, this is your p-type substrate and your diffusing n plus diffusions. Okay, here n plus diffusions, here also n plus diffusions. Okay, if you see here, there is a cross coupling occurs because of this different materials. Here n plus material, here p, and here if you see here well, okay, this is p, here well is n, and here p plus diffusions. So p and p. Okay, there is a interconnection between p and p. Okay, forming okay some losses. Okay, forming some losses p and p transistor, and okay this intercoupling between these materials okay opposes the flow of current. Okay, because of that there is a okay threshold voltage changes. Here threshold voltage it should be low, it should be low, but due to this intercoupling between these materials okay these layers okay there is a changes in the threshold voltage. Okay, due to this intercoupling between these materials okay this phenomenon is called latch up. Okay, this phenomenon is called latch up because of this intercoupling between these materials. Okay, to avoid this okay this latch up problem in the NL or PVL process, okay, we will go for twin tub process. Twin tub, twin tub process or twin well. Okay, twin well process. Okay, now I will share my screen. Yeah. Basics of twin tube, we can call it as a twin tube or twin tube or twin well fabrication process. Okay, here we will use two wells. Okay, in this we can use two wells to form these NMOS and PMOS transistors. Okay, as I told, to avoid those latch up issues, okay, we should fabricate NMOS, PMOS by twin tube fabrication process. Okay, after fabricating the using twin well fabrication process, okay, the structure will be like this. If you see here, structure will be like this. Here, forming two wells, N well and P well. Okay, here N well, P well, same procedure, but taking the two wells and before that forming these wells, okay, we are forming one layer. Okay, this is epitaxial layer. Okay, it is like a insulation layer. Okay, so that there is no coupling between these materials. Okay, then we can avoid this latch up problem. Okay, now we will see step by step. Here we will take N type substrate. First N type substrate. Okay. After that we will deposit epitaxial layer. Here the resistivity of substrate should be higher. Okay. So that uh, current conduction in that substrate may be low. Yeah, higher the resistivity, less is the current through substrate. This point. Then we should grow N plus layer epitaxy. Okay, you are forming the epitaxy layer. Epitaxial layer. This is epitaxial layer. That is having lesser resistance compared to substrate. Okay, comparing with substrate, this epitaxial layer having less resistance. Now we can deposit oxide layer, silicon dioxide layer here. Okay, silicon dioxide layer. Here substrate is subjected to oxidation and we grow SiO2 layer. Here SiO2 layer, oxide layer. First substrate, N-type substrate, epitaxial layer. Okay, forming, depositing, then SiO2 layer. Okay, the next step. Okay, now we need two wells, N well and P well. Okay, for that, okay, we need to remove this SiO2 layer. We have to form two windows. Okay, one, okay, year one and year one. We need to form two windows to, okay, make the wells P well and N well. Okay, why we are forming this well here? Because to avoid the latch up, means to avoid the intercoupling between the, here we are forming N type substrate and P well. In that we will deposit some N plus diffusion. So okay, there is a chance of coupling between these semiconductor materials. Okay, that's why here forming, okay, depositing some insulating material, epitaxial layer. Okay, here we are making wells so that there is no interconnection. Okay, SiO2 layer is etched using masking. Okay, here this SiO2 layer is stripped away, means removed by using the masking process by applying UV rays. Okay, wherever the window we want, there we can use mask. Okay, when we apply this UV rays, this photoresist material will be softened, then we can remove the our required area portion, we can remove. Remaining this layer will be same as it is. Here two windows are formed, one for N and another for P well. Okay, if you see here P plus diffusion. Okay, after forming P well here, after forming P well, okay, now we need source and drain. Okay, just I'm drawing. This is per gate, this is per source and drain terminal. Okay, for the purpose, okay, diffusing the P plus diffusion. Okay, P plus diffusion. And over here applying UV rays. Now here okay, using mask here, P plus mask, P mask. Okay, so that here okay, P plus diffusion here stop here, should not diffuse into this area. Okay, P plus diffusion will be formed only in this well. Here N plus diffusion. Okay, here diffusion, using diffusion we are making the wells. Okay, here diffusion is what? Here what is diffusion? Okay, at high temperature, okay, just keeping this vapor in one furnace at high temperature. Here, okay, this N plus diffusion means N plus semiconductor material will be diffused into this vapor. Okay, this epitaxial layer. Okay, based on the time and concentration, the thickness and depth will be formed. Okay, during this N plus diffusion, here we are closing this, okay, by using photoresist mask. Okay, after forming this P well and N well, okay, we need to form the diffusions for source and drain. Okay, source and drain. Before that we need to form the gate. Okay, gate, then source and drain terminals. Second window is covered by photoresist mask, then N-type impurities diffused to form N well. Grow thin silicon dioxide layer by thermal oxidation for gate terminal. Now before forming the source and drain, okay, now we can form the here gate. You can form the gate. Okay, grow thin silicon dioxide layer by thermal oxidation for gate terminal. Now after this step, you are forming the, okay, thin oxide. Okay, thin ox, we can call it as thin ox. Okay, here if you see here gray color, here gray color, that is thin oxide, thin silicon dioxide layer by using thermal oxidation. Okay, here thermal oxidation means okay, at high temperature, okay, we will allow oxygen in the furnace to deposit these oxygen ions, okay, layer by layer to form this thin ox layer. Okay, after depositing thin oxide layer, we can deposit gate. For gate terminal we will use polysilicon. Okay, polysilicon we will use. Grow polysilicon layer for photolithography and patterning making. Okay, using photolithography process, we can form the polysilicon for gate terminal. here. Okay, now if you see here, that gray color. Okay, okay, this is here small, that line indicate the thin oxide, and this one is the polysilicon for gate. Here also same, P well N well same. Okay, now here the before step. Okay, we deposited this polysilicon over all surface. Okay, the previous step we see. Yeah, here if you see, this polysilicon is here, polysilicon is deposited over the surface. Okay, after using patterning, photolithography and patterning, using some mask. Okay, wherever this gate terminal polysilicon is needed. Okay, there this it will be present, remaining area will be etched away. Here if you see, uh, here only here present, means this is for two gates, one is for NMOS, one is for PMOS. Okay, remaining this polysilicon material will be etched away. Okay, strip off. Now after forming this, okay, gate, we need to diffuse the source and drain. Okay, source and drain. Yeah. Okay, here in the second figure if you see, okay, P plus diffusion. Okay, here P plus diffusion we don't want here, so using we are applying some mask here, and here allowing UV rays. Okay, P plus diffusion, here P plus diffusion, so you will get P mass here, P mass. Okay, next step we will close here, we will use, okay, other mask, and we will here we will apply N plus diffusion. Here P well covered with photoresist mask and P plus diffusion is done to form source and drain regions. Yeah, here N plus diffusion to form N mask. Here photoresist mask is covered. Okay, N well covered with photoresist mask and N plus diffusion is done to form source and drain region. Okay, next after that we need to give metallization for the interconnection. Okay, metal diffusion is done for contact formation. For contacts, okay, we need to form the external connection. Okay, now we will deposit metal. Okay, this is metal. Now we need to separate it. Okay, this is for gate, this is for, okay, drain, source. Okay, now the next step we can remove this metal. Uh, Here you see, here, okay, after forming this one metal, okay, now we can remove the, okay, unwanted areas, means gate between drain and gate and source, we can remove this metal. Now we can form the connections for gate to drain and source. Metal diffusion is done for contact formation. Metal etching is done. Okay, here unwanted metal is removed by using etching. Contact formations for source, drain and gate is done. Okay, this is the twin well process or twin tub process. Means taking the two wells using epitaxial layer. Okay, this is twin tub inverter. If you see here, twin tub inverter. Yeah, here gate. Okay, gate we will use polysilicon. Generally this. Okay, this is inverter. Okay, in inverter, somebody is joining. Yeah. Okay, in the CMOS inverter, this structure will be like this. Yeah, this is CMOS inverter. Okay, transistor diagram. This is V out. Okay, this is V in. Okay, first top transistor is NMOS transistor and down transistor is no. Top transistor is PMOS, down one is NMOS. Okay, here this source and this drain are connected to give output, and here drain is connected to VDD. Okay, here VI. Okay, no. Here, if you see here the PMOS, okay, this is source. Okay, these both are drains only. Okay, these both are drains, and this is source. This is gate. This is also gate. Here, two drains are shorted to give output, and the source. This source is connected to most positive terminal, that is VDD. In the NMOS, the source is connected to most negative terminal, that is ground. Okay, here two gates are shorted for the input Vn. Okay, this is CMOS inverter. If you give input 0, you will get output 1. If you give input 1, output 0. Okay, that is the that we are considering here. Okay, twin tub inverter. Now here see, here annual means here forming PMOS. Okay, PMOS. Here PWL means NMOS. Okay, NMOS here making, and here PMOS. Okay, okay, you are taking N-type substrate. Okay, this line is indicating the epitaxial layer. Now here, see, here gates are shorted to give input Vin. Here gates are shorted to give input. Now here output is two drains are connected. See here, two drains are connected, that is V out. Here two gates are connected, that is V in. Here two drains are connected, that is V out. Now here VDD is okay. Okay, this is PMOS. So this upper top transistor is PMOS, and this is source. Okay, source and bulb is connected to most positive terminal. Okay, most positive terminal, and here PMOS, here NMOS, here source. Okay, this one source is connected to most negative terminal or ground. And here if we observe here box, okay, that is you can call it as a bulk or body. Okay, that is also always connected to ground or VSS. Here also if you see here this one, this is also bulk, or body, that diffusion. Okay, it is always connected to most positive terminal VDD. Okay, this is tin top inverter. Okay, next. Okay, if you see here now CMOS fabrication. Uh, okay, I told there are several steps: P-well process, N-well process, tinter process, silicon on insulator process, or SOI. Okay, okay. Now till now we have seen P-well process, N-well process, tinter process or twin well process. Now last one is the silicon on insulator. Okay, SOI means it represent the okay, okay, it is a prominent emerging CMOS process, and okay, as here as the name suggests, it is a process where the transistors are fabricated on an insulator. Means this transistor on insulator. Here insulating material or maybe silicon dioxide, okay, silicon dioxide or sapphire. Here silicon dioxide means that is one of the insulator. Okay, we can use sapphire substrate or silicon based SiO2 layer. Okay, that is the structure here. Here sapphire. Okay, one of the insulating material. Okay, sapphire. Here SiO2, buried oxide. Okay, yeah. Means in the previous substrate we have used P-type substrate, N-type substrate, but in the SOI process, okay, silicon and insulator process, okay, you will use insulator as a substrate. Okay, using this process we can avoid latch up problems. That issues also we can eliminate. Sapphire substrate. Okay, in sapphire substrate technology, a thin layer of silicon is formed on sapphire surface. Now, see what are the advantages of SOI, silicon on insulator. Okay, lower diffusion capacitance, smaller parasitic delay. Okay, lower dynamic power consumption. Here threshold voltage variations are smaller, and we can eliminate the parasitic bipolar devices. Okay, next technologies BiCMOS. Okay, here BiCMOS is what? What is BiCMOS? Okay, bipolar. Okay, CMOS. Okay, here in the CMOS technology, okay, we have some advantages, and in the bipolar technology, we have some advantages. Okay, to incorporate these advantages, bipolar technology. Okay, we will uh, merge this bipolar, some of the advantages to form this BiCMOS, okay, process technology. Okay, by using this bipolar technology, we can enhance the, okay, performance of the device by using some extra cost, some extra complexity. Now, mass transistors have limited load driving capabilities because of limited current sourcing and sinking abilities of P and N transistors. Here, bipolar transistors provide higher gain, better noise, and high frequency characteristics than mass transistors. Okay, because of some of the special advantages of BJT, we are incorporating this BJT technology in the CMOS to form the BiCMOS technology. Okay, here if we see the structure, okay, this is a plain view. In this technology, because CMOS, we will use PMOS, NMOS. Okay, okay, CMOS, we will use PMOS and NMOS, but whereas in BiCMOS, we will use transistor, BJT transistor. Okay, you will use bipolar junction transistor, that is, okay, NPN. Means we can forming the NPN transistor in the CMOS. Okay, that is called bipolar complementary metal oxide semiconductor. Okay, here this your diagram shows the only plane view to show the uh, NPN transistor. Okay, here just this is collector. Okay, now we will continue in the next class.